Welcome back to another lecture on quantum field theory and quantum entanglement. So, before going to the next lecture, because in the last class we had already introduced a lot of new concepts, essentially formally established the entire weight of Feynman meaning method of Feynman rule calculation, Feynman diagram calculation, and we took a simple model essentially of interacting scalar theory. Essentially, it's called Phi-4 theory, and we started computing the amplitude, okay, and the amplitude to cross section. You guys can do it on your own. So the cross section of a phi going into a phi essentially at leading order in perturbation theory, and then I showed you how to do it in higher orders, and we already first looked at that essentially why it leads to complications. Before that, but we has justified, because we have been learning the interaction theory in great detail, essentially that its vacuum is not the same as the free field theory vacuum essentially. So when we are dealing, we had the interaction picture, which is a combination of the Heisenberg picture and the Schrodinger picture, and what what is the thing which we want to do with how do you justify the use of Feynman diagrams in this particular picture. So in the last class I justified it, but I just want to go through it one more time. So this is the Feynman rule calculation. We start with the Lagrangian and then write down these following rules from the Lagrangian, which is called the Feynman rules, and so these rules are nothing but so what is a propagator, what are the vertices, what are the internal external lines, incoming lines, and what are the external lines which are like outgoing lines essentially. And then we just started drawing the S matrix elements that for a given process we will draw all possible Feynman diagrams connecting the incoming states to outgoing states essentially. In this case there is only one particular diagram because there is only one vertex. So using the vertices and the propagators you will draw all possible diagrams which leads to that process essentially. If you have phi going into phi, so you have phi. So this is the only process you can, the leading order, this is the only thing which you can write down essentially. This is the only diagram you can write down, and this is equivalent to the vertex essentially, there is nothing else. But if you go to higher orders you can also draw like this a diagram, there could be other diagrams essentially. So you should write down all possible diagrams essentially. In the higher order, say for example higher order in the coupling constant in lambda, then you introduce virtual particles essentially which are off shell, and then you have to worry about the momentum. So you can think of this particular set of diagrams, okay, and yeah, so you can think of other possible diagrams also, yeah, say okay, yeah, this is equivalent to the diagram essentially, yeah. So yeah, you can think of other diagram, these are the yeah, this is okay, phi to phi there is this is the only diagram at higher order also. So we don't have okay, so these are the diagrams which you can start drawing, and then you start computing things essentially. And then we looked at the Fermi golden rules, which will be covered in your exercises essentially for both decays and cross sections. So we will use the Fermi golden rule and calculate the differential cross section, integrate over the angular momentum variables, angular variables, and then get the full cross section essentially. Now this is a question we asked last time, that how does one justify the use of Feynman rules, because we learned that the interaction theory is a complicated thing, and so then how do you use the interaction theory compared to say for example meaning in a free field theory, because you are just using Feynman diagrams and then calculating the amplitudes essentially. How do you know that these Feynman diagrams work, meaning these are the correct way of calculating it essentially, given the way that we learn the interaction picture and so on. So, and to that the main thing is that calculating the vacuum of the interaction theory and normalizing the Hamiltonian such that the vacuum is set to 0 essentially in the interaction theory, and try to calculate the Green's function in the vacuum, okay, in the interacting vacuum. And you can show that the Green's function in the interaction vacuum is nothing but the free vacuum time order product of all these things times the S matrix element essentially. Okay. So this I did not show you the proof, I said you can find it in Peskin and Schroeder and various other places. So this can be shown, and you have to understand what is this vacuum to vacuum transition with S essentially, what is this vacuum to vacuum. And this we have argued that this is nothing but all possible interactions which lead vacuum to vacuum are nothing but these vacuum bubbles. So these are bubbles which are called vacuum bubbles in which there is no external line. Okay. The important point is these are connected diagrams, but there is no external line essentially. Okay. There is no external, and this series is an exponential series, so you can go further and further and everything. So this vacuum to vacuum transition with the S matrix is nothing but all possible distinct bubbles exponentiated, these in terms of these diagrams, and the numerator is all possible connected diagrams. Connected means essentially at least one of the legs is connected to an external line, okay, one of the vertices, or okay, one leg is nothing but is an external line, meaning an incoming particle or an outgoing particle. So at least one of these legs is an external line in times this bubble again essentially. So this time order product times S matrix times 0 0 can be shown, that can be argued essentially is sum of all possible connected diagrams times this connected leg. And so this time order product finally essentially the Green's function finally this cancels off. So the Green's function is nothing but okay, the time order product of phi 1 phi 2 phi 3 times the S matrix of this one, or Green's functions or S matrix elements or any of these things essentially. So this sets your thing that if you have, so if you are calculating some amplitude in S matrix, say for example with n particles with momentum p1 to pn, another particles with p1 point, so you have S minus 1 which is, or the transmission matrix is 1 plus S, so you have S minus 1 here. This entire thing is nothing but your Green's function, which all the particles appearing in the Green's function on the mass shell, all the particles appear on the mass shell. This is the mass shell in the momentum space, okay, in the momentum space essentially. This famous formula is nothing but the reduction formula essentially, LSD reduction formula, which tells you that but you know that this is nothing but your connected diagrams, nothing but your connected diagrams as we have argued essentially, which each of them all possible connected diagrams with the external lines lying on the mass shell, with all the external lines lying on the mass shell is nothing but your S matrix elements essentially, and that is precisely the reason why the Feynman diagram approach works very well essentially. So the Green's function in the phase space with all the particles on the mass shell is nothing but your S matrix element essentially. Okay. So I hope I revised it and argued that the Feynman diagram technique is a very useful way of calculating thing essentially, without worrying about the full the details of the Wick's theorem and so on, and the interaction theory, the interaction picture the Dyson series and so on. So without that you can just bring out this particular thing, okay, calculate this thing. In fact, Julian Schwinger is supposed to have said that Feynman diagram method brings calculations to the masses. Okay, this is a very famous quote by Julian Schwinger, okay, who used a completely different approach to calculate the amplitudes essentially. So this the Feynman diagram approach makes life much easier in computing these things. Now so far we have only worked with scalar fields. Essentially we only worked with scalar fields and computed the cross sections, we had done the quantization and so on. So essentially now we start moving towards Dirac fields. Okay, we will stop the scalar fields. We have done the interaction theory, and this entire interaction theory and justification of Feynman diagram technique. Okay, we will use it, essentially keep it as it is, and now we will move to a different sets with this non-spin zero essentially. Okay, okay, other than spin zero particles essentially. So we will look for. We will start looking at particles with non-zero spin. So the first ones we will be looking at is Dirac particles. So in today's lecture, in the next 15-20 minutes essentially, what I will try to do is to revise because I expect most of you to know the Dirac particle essentially, the Dirac equation and so on. So I would like to revise the Dirac particles which have spin is equal to half, okay, and we would like to do the quantization of this particular field essentially, of the Dirac field essentially. Okay. So the Dirac field okay, transforms non-trivially under Lorentz transformations, right? Essentially it does not. What I mean by that essentially is that the scalar field is just a invariant quantity. Phi is an invariant quantity under Lorentz transformations. So just to remind ourselves essentially how does the Dirac field transform essentially. We will remember, okay, the Spinor representation of the Lorentz group essentially, okay, okay, and then we will talk about essentially, okay, we will just, I will not do the full details of the Lorentz group essentially. I will not meaning these are all covered in the previous lecture essentially. So, but I will just do recap essentially, okay, let me call it as a recap of the Lorentz group Spinor representation. Okay, etc. essentially. And so I would like to do this because at the end of the day, meaning, okay, after doing all the stuff, essentially we want to revise ourselves what the Dirac equation is essentially, and what are the solutions of the Dirac equation is, and these will play a role when we quantize the Dirac equation, the Dirac field essentially. So there are some subtleties involved in the Dirac field quantization, and the role of the antisymmetry is an important thing essentially, because there is the connection between spin and statistics, which I will state, okay, and when we start quantization essentially. So there is some subtleties when associated with the Dirac equation, okay, the quantization of the Dirac equation. But anyway, let's start with the Lorentz group essentially. The Lorentz group, let's what is it essentially? It's a bunch of transformations mu nu. These are Lorentz transformations. Okay, so you have x mu prime lambda mu x nu. So you can start with this, and then x mu prime x mu is equal to lambda mu nu lambda nu rho x mu x rho, and this put conditions on lambdas and so on. So essentially, but what is interesting when you are studying the group theory is essentially the infinitesimal Lorentz transformations. So this should be unity essentially. So this shows that lambda mu nu lambda nu rho is equal to delta mu rho, and that gives you, so this is nothing but invariance of dx square. So that means that invariance of dx gives you this condition, and this gives you several conditions essentially. So, okay, so you can take the trace, you can take the 0 0 element, and then you have the proper Lorentz transformations and improper Lorentz transformations and so on. So this entire Lorentz group picture will emerge from there essentially. So this I will refer you to the paper by the earlier lectures. Relativistic regime. Okay. In fact, Dirac equation is also covered in great detail. So here I will just cover basic things essentially. I will just do a recap essentially. So lambda mu nu, I can think in terms of infinitesimal Lorentz transformations. It's called delta mu nu plus omega mu nu. Now this is symmetric and antisymmetric parts essentially. So this is okay. We can do something called dividing it into symmetric and antisymmetric part, and this is nothing but antisymmetric. So this is omega mu nu plus omega nu mu will be 0 essentially. So okay, so this will tell you this is unity. So you have, because it's omega nu is antisymmetric, you end up having only 6 elements, okay, which are divided into 3 boosts and 3 rotations essentially. Okay, so this is nothing but omega mu nu has 6 independent entries. This can be seen just from the antisymmetric of the 4 by 4 matrix. Okay, 4 times 3 by 2 essentially. So these will be divided into 3 boosts and 3 rotations. And suppose if I call these generators, and so there are 6 independent generators. So this will have 3 generators, and this will have 3 generators. So this will be x, y, y, x, zx rotations, whereas boosts would be x direction boost, y direction boost, z direction boost. So you'll have something like M01 will be your boost. Essentially this will be some matrix with the elements like something like 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, whereas rotations would be something like M 1, 2, okay, mu nu, okay, 0, 0, 0, 0, 0, 0, minus 1, minus 1, 0, 0, 1, 0, 0, 0, 0, 0, 0. So I won't cover the entire the Lorentz group, but I'll just only mention a little bit. And so so what you'll have is omega mu nu in terms of these generators is nothing but half omega rho sigma m rho sigma mu nu. Okay, now what are these things? These are some just numbers, essentially some parameters. Okay, these are some rotations, some numbers, essentially some numbers which tell you the extent of rotation. So what we have written is, we have written the entire Lorentz transformation in terms of 6 generators essentially times some small parameters essentially in which takes care of this thing. And then there is the associated Lorentz Lie algebra which is given by m rho sigma m tau nu eta sigma rho m rho nu minus inner rho t nu tau minus eta sigma nu m rho tau. Oh, okay. So at the end of the day, after this is a Lie algebra, and essentially like a row, this thing, I'll end up having E is equal to exponential 1 by 2. This is the basic idea that you have. This is your 5-minute introduction to Lorentz group, essentially that the Lorentz group, every Lorentz transformation can be represented as like a Lie algebra or a Lie group, essentially with an exponentiation of generators. There are 6 generators times some small parameters essentially which tell you the extent of rotation or the boost essentially. So this gives you the clear picture. Now what we want to do is we want to connect this Lorentz transformation to something called the Clifford algebra. And that is given by Clifford algebra is nothing but 2 eta mu nu. This is simple Clifford algebra. Essentially gammas are these matrices. These are 4 matrices. Essentially gamma 0 is equal to 0, 1, 1, 0. This is one representation essentially. So gamma I is 0, sigma I minus sigma I 0, sigma I are Pauli matrices. Now, now this we want to find matrices, okay, which satisfies the Lorentz algebra, this kind of algebra, okay, this kind of algebra, okay, the algebra which we have shown, Lorentz Lie algebra, but they should be representations of this, essentially they should be representation of the gamma matrices. So it turns out there is actually, okay, there is, okay, and this is given by this thing which satisfies, where is it, S rho sigma is equal to 1 by 4 commutator gamma rho gamma sigma, and this is nothing but 1 by 2 gamma rho gamma sigma minus 1 by 2 eta rho sigma, essentially. Okay. Okay, and this satisfies exactly the Lorentz Lie algebra I have written here. So this is the fancy Lorentz Lie algebra. Okay, this is the fancy Lorentz algebra, and equivalently I have constructed a matrix S made up of purely gamma matrices which have nothing to do with Lorentz transformations, but what does it do? It has the same properties like this, meaning that means S has the same, satisfies the same Lorentz Lie algebra. Okay, so that means if we have S mu nu, S rho sigma, so S mu sigma, S nu rho minus S nu sigma eta rho mu plus S rho mu eta nu sigma plus S rho nu eta sigma mu. Exactly the same thing, essentially. Okay, exactly. So what we have seen, okay, if what we have seen is that eta is nothing but okay, so I should, eta is your metric tensor. Okay, G mu nu or eta mu nu is nothing but your. So you see that it satisfies exactly this relation. This also satisfies the same thing. So what we call it as S forms a representation of the Lorentz Lie algebra. Okay, S forms a representation of the Lorentz Lie algebra. So we now have that you can, so that means that S mu is the commutator of the gamma matrices forms a representation of the Lorentz group, and so if we find some particles essentially or some wave functions which transform with S, they, we know how they transform under Lorentz transformations. Essentially they form a representation of the Lorentz group essentially, and of course we have know those particles essentially. Remember psi of x, okay, is equal to S of lambda psi lambda inverse of x. Okay. Now, this psi is a 4 component Dirac Spinor S is made up of the same gamma matrices, commutator, and psi transforms a representation of the Lorentz group essentially. Okay. So, it is exactly okay. So, lambda and S of lambda are 4 by 4 matrices and everything really falls through essentially. Okay. Okay. So, something which transforms exactly meaning so the psi is nothing, you know what is a matrix, meaning you already know that there is a Dirac equation, there is a Dirac particle which transforms like this, like a S of lambda of psi inverse essentially, and the this forms a representation of the Lorentz group. But there is one caveat, representations of the Lorentz group are non-unitary. We will actually, yeah, there is some caveat which should remember, caveat. So, this is something we will remember essentially. Okay. So, this is how the Dirac field transforms, and okay. Now, let us remember what is the Dirac equation essentially. Let us start remember this thing. We can think of writing the action and so on. So before, okay. How to form Lorentz scalars and so on. So there is this 4 component spinor, if there is a 4 component spinor. Now, even if you do not know this, so even if you do not know how a Dirac equation transforms essentially, you can still write that, let us suppose, or suppose psi of x is some object, okay, there exists a psi of x which is a 4 component object. So, for example, there is a 4 component object which transforms like this for Lorentz, under Lorentz transformation. So, it forms a representation, and psi could be a 4 component object. Okay. Now, you see that this transforms into 4 component object, and now you can start looking at how does various products of psi transform under 4 component under Lorentz transformation. And what we want to do is we want to build a assuming that I do not know Dirac equation, you can do the reverse also. You can assume that there is such an object which transforms as because S of lambda I have shown that it forms a representation. Okay. You start with another algebra which is Clifford algebra, which forms a representation, and so I say that there should be an object psi, let me call it an object psi, which is called a spinor, and it transforms like this under the Lorentz transformations. And now we can look at the action which transforms under the Lorentz transformations, and you will see that there are these things called psi bar, which is nothing but psi dagger gamma 0, and from this you can build something called covariance essentially, psi bar psi, psi bar gamma mu psi, psi bar sigma mu psi, psi bar gamma 0 psi, psi bar gamma 0 gamma mu psi, psi bar gamma 5 gamma 0. Okay. sigma mu, psi, and so each of them has a name. This is called a scalar, this is called a vector, this is called a tensor, this is called a pseudoscalar, this is called actual vector. So these are all things which you already know. I will not spend much time on it, and in the end we can write the Dirac equation, the Dirac action Lagrangian is given by psi bar of x I del mu gamma mu minus m psi of x. Okay. So this is the Lagrangian. So this is the Lagrangian of the Dirac equation. So far in this lecture revised the Dirac the Lorentz group a little bit, and then we looked at how the Clifford algebra forms a representation of the Lorentz group, and then we wrote down the Dirac Lagrangian. Essentially we wrote down the Dirac Lagrangian. And the Dirac Lagrangian is a Lorentz scalar. Essentially all the Lagrangians are always Lorentz scalar, Hermitian, and real, or real and Hermitian essentially. Okay. So with this we have introduced a Dirac field. With this now we look at some solutions, a little bit solutions of the Dirac equation, and then we will start playing with the quantization of the Dirac equation essentially. So remember, in this course I assume that you already know Dirac equation and its solutions and so on. So here I am just doing a recap. So if you have not studied the Dirac equation, go back and study and come back to these lectures, because from the next lecture my recap will be very fast. I will just introduce you the u and v solutions, and I will just write down the orthonormality relation and completeness relations, and beyond that then I will next move to quantization of the Dirac equation and the subtlety T1 valid. Okay. Now, okay, thank you very much. Okay, I will stop here. Thank you very much. Yes.